Okay, welcome back everybody for the final presentation of the conference. We have, just before I introduce Alex, I haven't seen too many personal pleasures yet, and whilst it's not mandatory, it'll be quite nice to see how the events of the afternoon are shaping the way people think about what they're going to do next. So it'll be quite nice to see a few before the end of the session. So Alex is Thames Water. He's head of operational technology, electrical engineer, involved with a lot of commissioning on projects, and currently Alex is currently in his 5th year doing a PhD, sponsored by Thames Water. Not sure what in, but be useful to know that. But yeah, so at this stage, I'll hand you over to Alex, who's going to talk about improving operational efficiency. Thank you, Alex.
Thank you. Good afternoon. So pretty much the PhD that I'm doing is what I'll talk about today. Yeah, lots of experience kind of in the electrical world, being an ICA technician, being on the tools out in the field, fixing instrumentation, fixing pumps, fixing PLCs, fixing SCADA systems, and then work my way through into the company as head of operational technology. That's my day job. My hobbies, probably not so much a hobby, but something I managed to get myself into was doing a part-time PhD many years ago, which I'm just about to hopefully finish a thesis on. But actually, it's yielded some good results, and hopefully I can talk about those today. So if we go to the next slide, if that's all right. There you go. Yeah, so a typical PhD type title, Metaheuristic energy optimization of a water company's wastewater pumping asset base. You've got to put in lots of long words and expressions to try and make it sound more clever than it is, and I think I might have done that on this occasion. But it is a good project, and it has got some results. So next slide, because that's just the holding slide, and I'm conscious that this is last knock-ins. It's always a difficult slot, and I want to know, right, how can I capture everyone to make sure that I keep people hanging on right at the end, you know, for that last one. Though you all just want to, I mean, back in the day we used to get on the train, didn't we? And you know, I was always one of those ones at the back of the room looking at the door. I'm ready to go because I've got a 2-hour journey home. Hopefully, because we're all doing this remotely, you can crack on. But what I'll do is I'll plant a little nugget out there and say, if I could reduce your wastewater pumping catchment's energy bill by 50%, by a theoretical value of 50%, I hope that will keep a few of you on until the end. So I can at least sort of talk you through how I got there. Okay, so starting off, you know, there's loads of good stuff. Thames Water as a company, we consume 1.4 terawatts of energy per annum. We've got a good renewable offset. You know, we generate gas. We've got loads of real estate for solar panels, and we contribute back. We offset, so 156 gigawatt hours of energy back into that. We're moving more towards TOTEX whole life costing. It's not just a case of if we need to do more, let's pour more concrete, or if we need to do this, let's put in more pumps. It's actually sort of TOTEX modeling, whole life costing. How do we do things better with our existing asset base? You know, should there be a shift in directive the way we think? And so how can we control our asset base more efficiently? From my experience and my background with PLC controls and stuff, and being heavily involved with wastewater, my PhD looked at those wastewater pumping catchments. I started off my journey, you know, reading all this really interesting stuff about artificial neural networks and fuzzy logic and all these really fantastic black box devices that can go and do all this really cool stuff. And it was quite frightening for me because I come from the practical world, not the theoretical world. And I got myself in a bit of a rut where I was thinking, well, okay, fine, these black boxes do really good stuff, but you've got to fit them on pumping stations. We've got thousands of these pumping stations within Thames Water. At 2 a.m, it's always 2 a.m. for some reason, but at 2 a.m, when something goes wrong and your on-call ICA tech has to go out, he or she does not care about a black box full of fuzzy logic, full of artificial, neural networks. They just need to get that pumping station running. And so I kind of with that, I really wanted my research to be applicable in the real world. You know, once I've proven it in theory, I wanted it to be able to be deployed. So I want to use the existing control systems, you know, whether it's a PLC, whether it's an ultrasonic controller, whatever that might be. I wanted to use that. And so I had this epiphany. I'm going to not do anything that smart with ANNs or and colony optimization and all that really clever stuff. That does play a massive part in what it does. I just wanted to be able to deploy what I was going to do in the real world. So that's kind of what kicked it off. If we can go on to the next slide, please. So what that meant is, apologies, for me to go and play with a catchment, I was never going to be allowed to just go and play with a catchment. I wasn't, you know, you go to any ops manager and say, hey, can I start playing with the start levels of your pumps? I think we can get some benefits that, you know, I know where I'm going to be told to go. And so what I needed to do was go to my operational colleagues with some tangible evidence that the strategies that I wanted to employ were modeled. I had the ability to, you know, give evidence that if we run these control strategies or we modify these start-stop levels in any way, shape or form, there's going to be the benefit that I'm trying to yield, which is a reduction in energy and therefore, you know, a reduction in carbon impact. But also I'm not going to do anything silly like flood a manhole or flood a house, etc. And so it was very much, I needed to find a hydraulic model. And just very briefly, there's many catchments within Thames water. I wanted to pick not a huge catchment because of the time to do the modeling, the frequency, and I'll come into that in a bit. But it was also, I wanted to pick a catchment that had a significant amount of investment already in the telemetry system. So in AMP4, stroke AMP5, Thames Water deployed a load of Xylem, what they're called enhanced pumping station controller devices. And what those devices do, as well as just giving your native telemetry signals up to your regional SCADA, they were installed such that you can reset pumps, you can run, you know, they control the pump rather than the ultrasonic doing its usual measuring the well and triggering a relay to start or stop the pump. Actually, the 4 to 20 signal went into the telemetry device, and it was this telemetry device that made the decision to stop or start the pump. And therefore what that enables is for something to be deployed maybe higher level, that once we've got it all integrated in the whole catchment on these telemetry devices, we can start thinking about more of a catchment control strategy rather than the very insular, my pumping station only looks at my pumping station. I look at water coming in and I get rid of it out of the well. You know, it gave me that ability to say, okay, we can have this interconnected control system, as it were. And so that was what led to me selecting my catchment, which in this case was a one in the South Downs in Hampshire, a catchment called Borden. Now, I'd never done any hydraulic modelling before. I was, you know, coming in electrically biased, PLC control, whatever, have a look at the hydraulic model, did a bit of consultation with the hydraulic modelling team and quickly found that the hydraulic model had there was a real problem for me, whereas I'm used to being out in the real world in pumps and wells where the hydraulic level is measured with reference to the bottom reference of the well, and the pump will start at 0.9 meters, and pump 2, if it's duty standby or assist, will start at 1.2 meters or something like that, and then it will turn off at 600 mil or just above the pump casing, so it doesn't snore the pumps. Now, and that's how I always knew it. Now, when I'm presented with this hydraulic model, it's all done in ordnance datum, so it's done with reference to Newlyn down in Cornwall, and it has absolutely means nothing to me. 68.11 meters has no relevance on the actual control system. So I had to go out. And do something to correlate what's going on in the real world against what's going on in the hydraulic model. So if we can go on to the next slide, please. I actually went out. So within Borden, there were 33 sites, of which what I would say there are 42 pumps. Now, there's obviously more than 42 pumps, but within the hydraulic model, when we have a duty standby system in the real world, in the model, we model that as one pump, because if it swaps over to the standby, it's only one pump running, and for the purposes of of energy, I did put the assumption in there that they were both of the same power rating, and therefore if one's running, it's running at say 5 kilowatts, and if the other one's running, it's running at 5 kilowatts, and therefore only one could be running at any one time. So 33 sites, 42 pumps. I went out and I dipped every well. We took readings off of the ultrasonic versus the actual level versus the top of the biscuit. And so we put a yellow dot on every single site. And I got all that data of those wells ready to go. And then I had to employ a third party. So if you move on to the next slide, please. I had to employ this company to go out and just get me those yellow spots converted into meters above datum. So just the surveyors, I can't remember the name of it. It's like a theolodite, and the stick that you see the civil engineers, when they measure the heights and they get it with reference to Newlin, they got those yellow spots. So then what I was able to do was to convert all my start-stop levels, everything to do with that wet well that I was used to in the real world, was able to convert into meters above datum, and therefore put it into my hydraulic model. And I did that for all of my pumping stations within the catchment. Now, the really interesting thing was the model previously was built on a lot of assumed data. In places, it was really good. It was actually not that far off. In other places, it wasn't so good. There were some major discrepancies, but all in all, quite interesting that some of it was so close on, given that it was mainly assumed data. I think that's it. And so, yeah, we did that for all the pumping stations in the catchment. And so what I would say is move on to the next slide, please. As part of the surveys, I was also able to glean all the pump data. So this was something that we didn't have in the hydraulic model at the time. None of the pumps, in fact, none of the rising mains had been modelled. Within the ICM world, those pumps are landed on as a blob, and you have the manhole at the bottom end, which is essentially the wet well, and then you have the further up the way, the other well, the receiving manhole. But what wasn't modelled within these hydraulic models was actually the rising main, and so you don't have system curve properties, and you didn't have any pump curve properties. So by getting all the pump data plates out of the sites as part of my survey, I was able to get the head discharge curves from the manufacturers and put them in the hydraulic model. So that's what I did. If we go on to the next slide, please. As part of doing that, I was also able to overlay the Lidar data from one of the hydraulic model teams. So we got the Lidar data and we overlaid that. And so, like I said previously, where you have the existing manhole node, which is on the left, which would pump up to a, not using a system curve, it was just like this transparent system, and the water would appear at the other end. What we were able to do using the Lidar overlay and using some modeling with that ground level was model a sealed system, like a rising main, which had system curve properties, as well as having pumps with pump curve properties. And so the model is now in a position where it is really, really bang on, sort of reflecting what's going on in the real world. And so we can start to run that up and get some calculations out of it. If you could move on to the next slide, please. We did have a slight issue in that the power that was coming out of the model was mechanical power. We didn't have electrical power, and ultimately my PhD was all about reducing electrical demand. So we had to do some, in the early days, I had to do some really sort of laborious work, which was exporting megabyte, like 500 megabytes per model run per parameter. Now I was mainly interested in upstream head, downstream head and downstream flow to get my calculation right. Each of those matrices was 500 megabytes. I then had to take those matrices and use a calculation to calculate the electrical power that was coming out of each of those pumps. And it was very painful, and it broke several PCs. We built servers to try and run it, and ultimately I was getting to a point where it wasn't going to work too well, until such time as I basically came across a company they're called Enginesoft. They're a company based in the UK, and they write the API for the Innovise. So the Innovise ICM package has the ability to have these API hooks into it using Mode Frontier software. And so Mode Frontier is like it's another variant of Optima. I believe the chap from Anglian was talking about Optima earlier. Matthew, that is, he was doing some stuff with Optima. We were doing stuff with EngineSoft and Mode Frontier, but I think they're very similar packages. And ultimately, what we were able to do was use these API hooks to get into the back door of the ICM modeling world, which meant we didn't have to do anything in Excel. We didn't have to do all these matrices, using yet another third party like Excel, which is quite a heavy application to be doing that. You just want to put it into the background processes of the PC world and just let it run, so it's really lightweight. And so we did that. Yeah, I think that's that for that. So if we move on to the next slide, so this is kind of where I'm going into now, is other design spaces of how we did this. So, right, bit of a random slide. What I've got is like I said, I've got 42 pumps. So they're my sort of manipulated variables. I've got one objective, which is I need to reduce power. And so what we determined is that the rule of thumb when you're doing your original design of experiments is that the rule of thumb is it's the amount of manipulated variables times the objectives times 2. So that was 82. So for my initial design of experiments, what I needed to do was get 82 model runs, just from random parts of the design space, to give me a foundation to start working with. And so we looked at different ideas. We could use random modeling, we could use Sobel modeling, we could use uniform Latin hypercube modeling. And so with random, what you can see is that the red dot, the red circles kind of indicate lots of clustering, so you get repeat design space. It's a waste of time, and there's vast areas of design space not inspected. Between Sobel and uniform Latin hypercube, what I found there were areas of clustering. The Sobel one was nicely uniformly distributed, but there was areas in the middle that it didn't explore. There were patterned clustering up there. And so with the uniform Latin hypercube, there were a couple of areas that were quite left out. And if I'm honest, there was a little bit of guidance from EngineSoft to say you'll probably get a better result with uniform Latin hypercube anyway. So that was the one we went with. And so what that did was ran 84 model runs of our revised model. So we've got the model, we've updated it so it's as near on the real world as possible. And what we want to do ultimately is start turning, manipulating the start levels of each of the pumps, so that ultimately by kind of throttling it back, by saying don't start just yet, start a little bit later, use that natural capacity within the network, we can reduce pump starts, we can reduce energy, we can use the natural, we can treat this as a collective system. And that was what we did. So those 84 runs were allowed to run. If we go on to the next slide, please. Ultimately, the mathematics that governed our model were for every pump, what we want to do is reduce power without any flooding. All right, that's it. Really simple. Reduce your power output from the power calculation as much as you can. That's the optimizer. Reduce it and don't flood anywhere. That's your only constraint. And so we did that with the uniform Latin hypercube. The 84 model runs were allowed to run, and the results will show a bit later, but it doesn't really matter. I can tell you now, none of them worked. They all flooded. Those first 84 flooded. There was the optimizer wasn't allowed to do any. Well, it went crazy. Didn't know how to control it, but they all flooded, and that's okay. That wasn't. I mean, at the time I was a bit nervous about it because I was wondering if we were ever going to bring it in and get it into a state where we would start seeing some tangible benefits, which we did. Next slide, please. This is just a workflow. So ultimately, I was talking to you about EngineSoft and the Mode Frontier. So this is kind of like similar to the Optima environment. You really simple to put together. Some constant parameters along the top. The scheduling starter on the left, so the clock with the arrow, into the ICM node, which is the API hook into the hydraulic modeling package. Some outputs. We've got the whole network stored flood volume and the whole network lost flood volume. So either of those outputs, if any one equals greater than 0, it's a failed constraint. We then export the downstream flow, the downstream total head, the upstream total head, put them into the pump power calculation script, run that, get our pump power, and then we use our pump power target. Obviously, we're trying to reduce that, so that's our objective, and we just run the process iteratively. And so, if we move on to the next slide, because this is the one that really kind of gives us the results. So what you can see there, everywhere on the graph where there is like a coloured blob at the end of one of those design lines is where we've had a result, a feasible result. So i.e. we didn't flood anywhere within the catchment. Everywhere else where it's just a grey line that goes up to a grey line and there's nothing, we flooded the catchment. Okay, so we've got to ignore those. And like I said, the first 84, they all flooded on the design of experiments. But not deterred by that, I was keen to move away. So we moved away from just running random stuff using the design of experiments, the uniform Latin hypercube method, and what we wanted to do then was put it into an optimizer. And this is kind of like the multi-strategy idea. We used a proprietary system called a pilopt, and it was explained to me. It's very much like if you've got a blind mountaineer on a mountain, and you want to get him or her to the top of that mountain, you've first of all got to you want to get them on the top of the highest mountain in the range of mountains. You first of all got to get them on the peak that is the highest peak. First of all, it doesn't matter if you get them high up the peak, just get them on that mountain that has the highest peak first. That's your global optimization. Get them on there first. Once you've got them on there and you're satisfied they're on there, then start to move them up to the top, and that's local. So once you switch from your global to your local optimization, that's when you're really getting it up, fine tuning it to the top. So we used that pilopt, which was a mixture of global, local, and around about the 101st run, what you'll see is that we got a feasible result, and actually that result was a good reduction against the baseline. So the baseline was the red X at the top, which is about 21.5 kilowatt, 21,500 kilowatt hours for the month of July. I think it's probably worth pointing out that I did this with no wet weather profiles. The sort of the most normal operating time is dry weather flow. It was always my opinion that if a deluge comes down, we'll use the backup float control systems just to put the system back into normal control, because any logic that I wanted to put into this would only be for dry weather flow at this stage. It also meant that model runs were a lot less complex, because when you start putting rain profiles into the models, it makes them a little bit more computationally heavy. So we did it for dry weather flow only. So against the baseline, the first pilot one brought it down to about 14,000 kilowatt hours for the month of July, which was really good. And as you can see on the graph, it was a little bit in and out, and it seemed to hover around the 14,000 kilowatt hours. There was a couple that were a bit higher, and then there were a couple a bit lower just towards the end. That then really we got a drastic reduction of just over 11,000 kilowatt hours, which was almost a 10,000 kilowatt hour reduction in power for the month. So that's the 50% that I talked about at the start. After that, what I wanted to do is, right, I've used this proprietary global local algorithm. What I want to do now is see if I can fine tune it with a local algorithm. So that's when I moved on to the Levenberg Marquardt algorithm. And as you can see, it just flatlined. It really didn't yield any more. It was trying lots of different things. It did actually win the day at the 383rd, which is highlighted in very luminous green around the 400th iteration, as you can see on the graph. And that was the one that hit the main reduction. And overall, so the combination from the multi-strategy and the Levenberg Mark algorithms reduced the power consumption from 21,500 to 11,200, which was a net saving of 10,240 kilowatts hours for the 31-day period. Converted into monetary terms, using a business tariff rate of 12.93 pence per kilowatt hour, that equated to a potential capital saving of £1,324 per month for the catchment trial. Okay, so let's just revisit that. There's a couple of things there that I need to make you aware of. One, the upper boundary consent level was the top of the well. So I let the optimizer allow the levels within the wet wells get as high as they possibly could without flooding. Now, as a shift controller, as an operator, I'm never going to want to be running that level of risk. The straw that breaks the camel's back. If a drop came down, it could cause an issue. So when I said 50% is theoretical, but actually, if we were to strike a balance with, well, how much risk are we prepared to take? If we were to just lower that trigger point to, say, a meter below the biscuit level, we would still have a huge saving. Let's also focus on the fact this is such a small catchment. The pumps in the catchment, like 42 pumps, they were generally 7.5 kilowatt devices. So there were a couple that went up to 15, and I think on 3 pumping stations we had a couple of 40 kilowatt drives. But the scalability of this, in terms of some of those catchments in London where we have pumps that are 500 kilowatt drives, there is something that we can really do here to reduce the energy. And so that was it. That was kind of really, it was a short, sharp, snappy presentation of what we've been up to, trying to optimize using our existing assets, with a focus on not throwing in black boxes. Use our existing telemetry assets to do it. Yes, we have to use the optimization sequence in the background to link it with a hydraulic model. But kind of the buzzwords, and if you look at the Gartner hype cycle these days, digital twin, this is very close to that kind of digital twin element where we can start maybe thinking about, okay, how do we start really taking this forward? And so for me, I've kind of done the research, and now we're in a place where we're having different conversations with different people about, right, how do we make this into something that we can take forward? And yeah, it's exciting. And I would like to be able to update you all at a later date if and when there's an uptake and we take this into the real world, the applied world. But for now, that is it. So I will thank you all and welcome any questions.
Okay, thanks for that, Alex. It certainly opens up eyes really as to what can be done to make networks more efficient, and there are many ways to reduce carbon emissions, and just being more efficient in the way you consume power for no loss, then, so no detriment to the level of service. Just doing things more efficiently makes considerable savings. So I was just wondering what the plans are now. Is it to extend this to the whole of Thames Water's networks, or maybe even clean water systems to use that optimizing approach?
I would like to see it happen. So the real bugbear for me is that this was my PhD, and my day job is nothing to do is operational technology, and so I'm trying to do it. The other major hurdle for me personally with my research is that actually in Borden, if anyone knows Borden, there's been a significant housing project happen down there. And so actually, if we really wanted to apply it, we would have to redo the model, and it costs money. When you're doing it as a PhD, you can get evaluation trial licenses of these software systems. So Mode Frontier, I was very lucky enough to be given demo licenses for the purpose of academia. Similarly, the ICM exchange, which is we've got obviously all the licenses for ICM and hydraulic modeling, but to be able to have those third-party applications, those API hooks that go back in, you need to run the ICM exchange. Again, that's we're talking hundreds of thousands of pounds per annum of licensing, from what I'm led to believe, and the support that goes with it. So there are going to be cost trade-offs. That I think we're going to be getting there. I don't know if it's going to be done. And if I'm brutally honest, if I had my time again, I wouldn't have focused on energy as the objective. I would have looked because yeah, fine, you can reduce energy in the pumping catchment, but actually, if I'd used my optimizer to smooth the flows going into the sewage treatment works, so that you don't have oscillations and peaks and troughs in water, but you know, if you have serious sort of spikes in water going into the treatment works, you essentially can short circuit your primary clarifiers and push a load of water through into your aeration lane, and then you're just aerating water. You know, and we know that aeration is, you know, electrically the biggest burden on any waste companies on the bill. So I would actually like to maybe revise it and say, right, let's make the objective keeping the flows into the works, you know, within these boundaries, so that we're not short in the primaries, so that we're not pushing water through into the aeration lane. But what this research has shown is that you can do things like that, and actually, you know, that's fingers crossed. I don't want to do another PhD, by the way, so I'm certainly not going to do that. I'm just going to write this one up and be done with it. But it's food for thought. It's definitely part of the thesis at the end. We'll touch on that, and you know, I'm hoping that there'll be an uptake to do that, because I think that's more than achievable, and can definitely bring some real benefit and a massive carbon reduction.
Yeah, I mean, hopefully the work that you've done won't be lost, and someone else can pick it up and develop. I suppose the ultimate goal would be the digital twin for the network, so that you can see everything that's going on.
Yeah.
So that, you know, the sort of maths that you've developed for this trial could be used on a much bigger scale, but maybe you need some fresh energy or a bigger team maybe in one. But
I think that might be it. Yeah.
Yeah. Okay.